Hello, everyone. Welcome to the first installment of your Math 320 videos. I am Professor Wang, in case you have forgotten. This week, I will be calling week 0 since the video lectures will only be about an overview of this course and some review of material you should have seen in prior classes. Before we get started, since this is the first lecture video, let me remind you to spend some time reading the syllabus. The syllabus can be found on the D2L page for this course. While I will give, or perhaps had given, depending on when you are watching this video, on Wednesday a synopsis of the most important aspects of the syllabus, I will not be able to go into full detail on everything. The syllabus is a bit long, around 15 pages, and contains detailed discussion on class policy and procedures. Please do take the time to look it over. If you have any questions on the syllabus, a good way to get clarification is to ask on our class's Piazza forum. That way, other students will also benefit from any answers I may give. If you haven't done so already, please pause this video now and go sign up for your Piazza account and join our class's Piazza forum. That's the end of the administrative announcements for now. Today's lecture will focus on giving you an overview of what this course is about and telling you a bit about what I hope you get out of taking Math 320. Let's begin. We start broadly. What is real analysis? Real analysis is the branch of mathematics that puts calculus on sure footing. This first point I explained a bit more in the syllabus. Basically, the original invention of calculus made use of an intuitive understanding of infinitesimals. And how we teach calculus even now still appeal a lot to this intuition. In the 19th century, however, mathematicians discovered that sometimes intuition can lead us astray. They then formalized calculus by replacing infinitesimals with a certain concrete procedure. This replacement allows us to reason consistently with both the infinitesimally small and the infinitely large. The subject of real analysis concerns this development. In Math 132 and 133, this being Calculus 1 and 2 at MSU, you learn how to compute by applying certain techniques. As examples, you were taught how to apply the intermediate value theorem for continuous functions. You were taught how to use the chain rule to take derivative. You were taught how to use the comparison test to decide if a series converges. For many students, these tools are a jumbled mess of facts that require memorization. In this course, you will learn why these tools work and hopefully develop a coherent picture of how everything fit together. So, having described real analysis in the abstract, let us talk about our course. The central focus of our course lies in answering one particular question. What makes the real number line R a continuum and not just a collection of points? If you've read Euclid's geometry, you will see that it is assumed that a line is made out of individual points, but no mention is made on how the points are glued together. We will be answering this question through a mathematical concept called completeness. This turns out to be the distinguishing feature between the real number line R and the collection of rational numbers. The rational numbers can have arbitrarily large denominator and are packed very close together. And in one sense, the rational numbers have no gaps, since between any two rational number, we can always find a third one. This is, by the way, called the Archimedean property, and we will touch upon this at the end of week 1. But in a sense, the rational numbers is missing the glue, that it is a collection of points and not a true continuum, a line. This missing glue is the notion of completeness, and this is the most important mathematical concept you will take out of this class. Now, once you've mastered the concept of completeness, we can use it to build a proper understanding of calculus. We will start by making sense of what it means to take limits. We'll first take limits of sequences of numbers, since the definitions are slightly easier to grasp there, and we move on to understanding limits of functions. Notice that this is in the reverse order as in your typical calculus class. Sequences and series form the second half of Calculus 2, while limits of functions is the first thing you see in Calc 1. The concept of limits of functions will then be used to make rigorous definitions of continuity and differentiability of functions. Having given you the big picture, let's give you a quick overview of the specific topics and keywords of this course. The first third of the course will be on the completeness aspect of the real numbers. Three important and closely interrelated concepts are the Archimedean property for the rationals Q and the reals R, the completeness property of R, and the notion of suprema and infima of sets of numbers. This last notion is somewhat confusing to many students, and we will spend quite a bit of time discussing it. The next third of the course concerns limits and sequences. We first give you a precise definition of convergence for sequences and discuss the properties of limits. Next, we talk about Cauchy's criterion. This is an interesting idea in mathematics. For the usual definition of convergence, which you may have already seen in Calculus 2 or maybe in Math 299, to prove that a sequence converges requires knowing what it converges to boot. This seems like a chicken and egg problem. If I know the limit already, then I probably already know that it converges. Cauchy was able to come up with a way of proving that a sequence converges without knowing what it converges to. And this is his namesake criteria and is the better way of proving convergence of a sequence. This will be followed by the monotone convergence theorem, which you may vaguely remember from Calc 2. It is not overly emphasized in the curriculum of MSU, however. Next, a discussion of subsequences and the Bolzano-Weierstrass theorem. This theorem is an important theorem concerning the structure of the real numbers and is the foundation of a lot of analytical arguments having to do with convergence. We will close this discussion with the notion of limit superior and limit inferior. These concepts are a bit hard for the first-time students to grasp, but understanding them is crucial to understanding why, for example, the alternating series tests actually work in Calc 2. This notion is also very important for the definition of integrals using the Riemann method, though we will not talk about integration in Math 322, deferring the subject to Math 421. The final part of this course concerns limits of functions and applications. This starts from defining the limits of functions and continuity of functions. From there, we will give a detailed discussion of the intermediate value and extremal value theorems, both of which you should remember from Calc 1. We will close with a definition of differentiability of functions and a complete proof of the mean value theorem. Now we dispense with the content of the course. Let me share with you what I, as your instructor, view as the purpose of this course. What I hope you will accomplish in this course is primarily, first, gain a hands-on experience doing mathematics. By doing mathematics, I do not mean the sort of rote computation that you did in Calc 1 and 2. Here I mean solving problems through logical reasoning. You will be doing mathematics in a way that reflects a professional practice. Specifically, and secondly, you will make axiomatic deductions and be thorough about your reasoning. And thirdly, you will communicate mathematics both orally and in written format. I want to point out that these three are extremely transferable skills. Whether you wish to enter academia and go into graduate school in the pure sciences or go into industry in an engineering discipline, logical reasoning, the attention to details, the willingness to consider edge cases, and the persuasive presentation of your work are all valued skills. What we will do in this class, however, is to practice these skills through the study of real analysis. Notice that the primary accomplishments do not include content knowledge. This is deliberate. As a specific content of real analysis, I feel should take a secondary role in this class, in part because a lot of the facts that you will be learning in this class you will have already encountered in a different course. What we will be doing in this class is more trying to help you bridge the various calculus facts together through a deeper understanding of how everything works. So with that in mind, here are some secondary goals. First, you will appreciate the importance of qualifying premises. By this, I specifically refer to the hypotheses portion of a theorem and calculus statements that you've already learned about in previous classes. Those hypotheses are not just there for decorations. Frequently, if you omit even one of these hypotheses, the entire theorem will fall apart. We will understand this by building up for you an arsenal of examples and counterexamples. Now, if you have looked at the syllabus, this will be a large chunk of what we will do for the Friday in-class activities. Secondly, you will gain the ability to confidently manipulate infinitesimals and to translate such manipulation to rigorous justification when needed. In terms of the mathematical skills you should take out of this course, this is the most important as it underlies almost the entire subject of analysis. If you're comfortable with this task, you should be completely at home even with more advanced analytic subjects. Thirdly, you will gain content knowledge in real analysis. It is an analysis class after all. And finally, you will learn to prepare documents with heavy mathematical content. If not yet look at the syllabus, I will require all of you to type your written homework responses. There are certain practical aspects to this since I want to also implement blind peer-to-peer reviewing and blind grading of your work. But this is also a highly transferable skill if you will be working in any technical field. Please do take a look at your syllabus and see how you're expected to prepare your write-ups, and ask questions on Piazza if you have any. Well, that is it for this lecture. I'll see you next time.